Hello, everybody. In this chapter, we're talking about torque on magnetic dipoles. So the idea is to imagine a circuit. Now, the book shows two circuits, one that is a square and one that is a random figure. I'm actually going to draw the square, which I believe is a little bit uh, easier than the random shape, at least to begin with. So we have a square. Now, I'm actually drawing it, and we're looking down on it. So this one is actually the y and x y and x um, plane, and we have a magnetic field that comes out of it. Well, comes out, as you can see right here. I'm actually gonna draw it in a y and z diagram. So I have z on top here, y here, and I'm gonna say that it's a little bit bent over the initial magnetic field. So the magnetic field, as we said, points up along the z-axis, and we have our, actually I'm going to draw with a different color so it's a little easier to see, green. We have our plane with current that is flowing in a anti-clockwise direction. Okay, and of course you can already see that the torque of this um, of these the torque that is affected, the torque that affects this plane is going to be equals to, well, the formula for the torque is B, let's call torque N, is going to be equals to the R cross B. In our case, R is going to be the side of a square that I'm just going to call A. Now, actually, the book doesn't, it's not a square, it's a rectangle, but I just say a square for right now. So it's going to be a square, it's going to be a side, so it's going to be A vector cross B. And as you can already imagine, using the cross product, we can just rewrite it as A B sine of theta in the x direction. Now, why sine of theta? Well, sine of theta is what we call the angle that is created between the normal of our plane and the magnetic field, which is actually be the same over here. Okay. Um, Now, in my case, it's 45 degrees. I just made it so it looks nicer. It's not always going to be 45 degrees, so it just looks nice in this case, but it's not going to be like this all the time. Anyway, so we said, of course, well, sorry, this distance is equals to A. Oops. All right, and this is the torque force, very easily. Now, the force that is acting on this plane is actually going to push on this side on the right and on this side on left. Now, how do we know this? Well, that is because we have to use the right-hand rule for the current and the magnetic field. So, if you use the right-hand rule for the current, and we imagine the we imagine that the um, on the left side we know that the on the left side we have the current flowing towards us. I'm gonna write it in the addition, and this is away from us. We know that thanks to the right hand rule, it's going to be one pointing toward the right, one pointing toward the left, and they're going to be the same magnitude. So it's going to be the same in the end, right? Okay, so the torque is going to be a different thing than the force. We just know that the force will actually not have any effect along the y-axis because they will cancel each other. Now, the book mentions that actually we have a slight difference in they're not just going to cancel each other, they're actually going to stretch the dipole a bit, but we don't worry about it right now. And the force acting on acting on our dipole circuit is going to be equals to the current times the length of one side. Let's call it B. Actually, B is this side right here. Now it looks same in my drawing, but just to keep things easier, IB and capital B. Now, if you haven't doubt about this, you can simply think about it as MVB. Sorry, my bad. QBB, and which is the force for the formula for a magnetic force. And how do we get there? Well, we know that V is equals to a length over time, so we can substitute it in there. We will get Q equals to V over T times B, and then we rewrite it as Q over T times V times B. Sorry, this was the length L, and Q over T is equal to the current. And now our length is actually equals to B. So we know that it's going to be equals to, oops, what is what? Okay, so we're going to have current times the length times the magnetic field. As you can see, we just proved it again. So now, N, our torque, we said is equals to, oops, I don't know why I wrote B. It would be equals to RF or AF, in this case, AF sine of theta. So we can rewrite it, since we know that F is equals to ILB. We can write it as A times I times L times B times sine of theta in the x hat direction. It'll be a cross product, so we'll just simplify that. And if you think about this part right here is going to be equals to the magnetic dipole moment of the loop. So it's going to be equals to MB sine of theta, the x-hat direction, or put simply, M cross B. These of course are vectors. And so we go back to the cross product, and instead of writing it as R times F, we write it as R cross F, we write it as M cross B. It's not a very easy chapters. However, you can remember that we had the same torque on an electric dipole given by an electric field, which was P cross E. So they are very much similar. They are the same formula pretty much, just changing from a electric field to a magnetic field. And that is the first part of the chapter. The second part is a little more complicated, so I'm just going to do it in another video.